Get ready to start, baby. Easy, baby girl. Hey, Jennifer. Only you so far.
I'm here.
Yeah, it's only you so far. I think I'm gonna have to go ahead and get started, even though it's past the time because it is optional. So I'll go ahead and get started. Do you have any questions before we do get started, though?
Yeah, do you have any plans for the first face-to-face yet?
Yeah, I did already. I just sent that out. That was the last sentence in the email I just sent out to everyone. So I have moved it. It's due on the 9th. That's the first online test. So I moved it back a week. That means I'm basically going to move all of the tests back a whole week, except for the last two within the last 2 weeks. I can't move those back because that's the end of the semester, but I'll move all the other ones back exactly 1 week. I'll make a change to the syllabus and post it anew and send you an email when it's up.
So a week from the, is that what
Yeah,
I'm
the
hearing?
online ones due a week from this Sunday. So it'll be the 9th instead of the 2nd. And then I got to go through and check all the dates and make sure they work.
Sorry, you guys have to be quiet. Sorry.
Yeah, then I got to go through and make sure all the dates work. But my intent is to go ahead and push all the face-to-face ones back by 1 week.
Okay.
Okay. Again,
That,
except for the ones at the end because we can't, like the final exam and the very last one, we might not be able to.
but I'm just taking it one test at a time.
That's cool. That's all you got to
Okay.
do. All right. Well, I'll go ahead and get started then. Remember, I want to make sure this is on video and recording for everybody. Is when you do come in, there is some chance that it's showing your name. So if you're, not wanting people to know your first and last name or see your face on occasion or any of that kind of stuff, make sure you let me know that and maybe change your username to just your first name and maybe the first letter of your last name. But again, I just want to make sure I got that out one more time to everybody. I'm trying to do that with all of them, just in case. There's actually been cases where I've known people that were literally in hiding. So if there's someone in hiding, from the mob or whatever, or an abusive, relationship or something, I want them to feel safe and I want them to be safe. So they just need to let me know, and they don't have to tell me what the reasons are. Okay. So I'll go ahead and get started. With chapter 18 finished, remember I said there was some very specific sections that I wouldn't be testing you on, but essentially all of them are fair game far as homeworks and practice tests. That's because I really like the material. I didn't necessarily want to cut it out, but I didn't really want to test you on it. I just wanted you to have the chance to learn it, make some headway in understanding it a little better on your own, and also make some headway on learning how to learn on your own. Since I didn't do much to cover it, your ability to make sense of it from just the reading, that's a whole nother skill that I definitely want my students working on. Almost called you my guys. So we're doing chapter 19 now. I'm going to, in fact, be occasionally using the book, but I just want to remind you that chapter 19 is heat and the first law of thermodynamics. And the sections thereof are, let me pull these up real quick so we can read them aloud or whatever. But these sections are 19.1, heat as energy transfer. The main thing I want to remind everybody about that is uh, we used to believe that heat was something that was contained within an object, and it was sort of like a liquid, and we called it caloric. That's where we got the idea of the calorie. We've since realized that that's not what it has. In some sense, all objects have what we call a thermal energy, or what your author's calling an internal energy. And in principle, that's all the types of energies that all the atoms and molecules have within the object. So if you have an object, which is like a box or some gas in a cylinder or a chunk of metal or whatever, those are all quote unquote systems. And if you added up all the individual types of energy that is inside of that, which includes all those different kinetic energies, as well as all the potential energies for the charges, because in an atom and a molecule, you have plus and minus charges. You have a Coulomb force that acts, which y'all haven't learned about yet, but it's like gravity. And just like gravity has a potential energy, it turns out that electric force has a potential energy as well. Uh, we also know there's energy, sort of like potential energy as well, stored in the nucleus. There's chemical energy associated with bonds between adjacent atoms, for instance, making up a molecule. All of those energies combined make up what we call the internal energy, and a lot of books call that U. In your text, they're calling it E with a subscript int, or just plain E. So the internal energy we're going to demarcate as capital E, and then occasionally I will write int down below it or just leave it off. Whereas, as I said, there is heat, and heat is actually better thought of as the transfer of some of that energy from one object into another object. So you can actually take some of the energy that is internal energy of an object, and because it's in contact with another object, if that other object is colder than the first object, meaning a lower temperature, then heat will spontaneously flow from the hot body into the cold body just because they're touching one another, and that would be heat by conduction. And that happens. And the fact that it goes from from a high temperature to a low temperature, that's actually a statement of what we call the second law of thermodynamics, one of which those statements is that heat will spontaneously flow from a hot body to a cold body. And that is in conduction, but it also works in general. For instance, the sun definitely puts out heat energy, and that heat energy can be sent out via radiation to outer space, which is obviously colder than the sun. And then that can actually send out that outer space, and the heat going through outer space can actually impact on our atmosphere, in which case it becomes like a conduction type situation to get it from the space into the atmosphere. And then when it's in the atmosphere, it can use conduction, convection, or even radiation to get to other parts of the atmosphere or within the planet Earth itself. So you might have noticed this. I know I did when I went away to college for the first time, which is weird. I would have thought I'd noticed this before, but maybe I'm just more sensitive now to temperature. But like one afternoon, I'm walking the dog, and it's like 4:30, 5 o'clock in the afternoon. The sun's kind of low. I walk around the end of my apartment complex, which is just one long building, like 6 apartments or whatever. And, I'm letting the dog use the restroom by the flower bed and all that good stuff. Or use use the bathroom. I guess he's not using a bathroom or a restroom. But anyways, my dog's doing his thing. And all of a sudden I feel all this heat, and I realize what it is. It's the sun has gone down, and end of the apartment building facing the sun had gotten really hot from the sun banging on it all day. And now, as the sun was going down, that heat was re-radiating out towards me. I could feel it. I mean, like if I had a sunburn, for instance, when I was out there, it actually made it painful because you could feel the heat hitting. So that is something that we will notice, is that as things get heated up, then they give off heat later. And that's exactly how the Earth works. When the sun sends its energy, it goes through a partial vacuum of space and then gets into our atmosphere, and then it hits our surface of our Earth to some extent after it's been filtered out by the clouds and the ozone and all the different bands that stop stuff. Some of which are very important, like the ozone layer can protect us from a lot of UV radiation that causes skin cancer and stuff like that. Uh, there's other layers of the atmosphere that protect us, for instance, from what we call the solar wind, which is charged particles that are actually being sent to us from the sun. But the main thing is it filters out, and some fraction of all that sunlight that hits the Earth's atmosphere will hit the Earth's surface. And it comes in characteristic of the temperature of the sun. So there turns out to be a frequency versus temperature distribution with any amount of heat or any type of heat coming from anywhere. And what happens is if you make a plot of that energy as a function of wavelength or temperature or something like that, you'll see that it actually comes up, has some peak. It's very sharp and straight up, almost straight up on one side, and then it crests over and then gradually falls off. That crest is inversely related to the temperature of the source of the heat. So the location of where that crest is, which means a very specific wavelength of that particular radiation, is inversely proportional to the temperature. When I say wavelength, it's inversely proportional. When I say frequency, it's proportional, but it's proportional to that wavelength. So the sun sends us heat with a peak that corresponds to the temperature of our sun, which is, around 6,000 Kelvin or whatever. And then our Earth takes that heat, just like my apartment building at the end of it, on a 5 o'clock in the afternoon. The Earth actually re-radiates that heat out as just like the building did, only again it heats it out with a energy spectrum, if you will, or a wavelength spectrum, if you will, that peaks at the temperature of the Earth's surface. So, 54 degrees Fahrenheit is roughly the surface temperature of the Earth on average, that sort of thing. So its peak would be shifted way over because the temperature is way lower than the temperature of the sun. That's what actually causes our greenhouse effect because the on the way in, the sun had one specific radiation associated with obviously an infinity of wavelengths, but the peak of it's actually at a very specific wavelength, and that very specific wavelength has very different travel restrictions in terms of going through our atmosphere than one whose peak corresponds to a wavelength that's 54 degrees Fahrenheit. So on the way out, the 54 degrees Fahrenheit radiation on its way out, it can actually be stopped by things that couldn't stop it before, and those things happen to be polyatomic atoms. So ammonia is one, methane is a greenhouse gas, water vapor is a greenhouse gas, carbon dioxide is a greenhouse gas, ozone's a greenhouse gas. And basically, that's sort of, if you want to think about it at the microscopic level, you can sort of imagine that there's vibrational modes associated with the atoms or molecules of those specific greenhouse gases. And those modes of vibration are comparable to the mode of vibration of the Earth's heat coming out of the Earth. And because of that, some of that heat can be absorbed by those molecules, and then they will start vibrating at the frequency that that radiation was vibrating at. And the energy that was coming at it before has basically been absorbed by that molecule. Now, later on, that molecule is, it's excited from all this extra energy it got. So, it has, for instance, electrons that have moved way out in their outer orbitals and all sorts of crazy stuff like that. But eventually it realizes, hey, I'm not all that comfortable having all this extra energy. So it just shoots it out in a random direction, just like any atom would. So when an atom has been excited in some sense by its electrons bumping up to higher energy levels, they're not going to stay that way very long because they always try to minimize their own potential energy, or at least that seems to be the way matter behaves. So the same thing's going to happen with this. Those whatever's causing that excess energy is going to stop eventually, and it's going to spit that heat that it had absorbed earlier. It's going to spit it out this time in a random direction, and a little bit over 50% of those random directions are a little bit under them, are under that 50% is back towards the Earth, and a little bit over 50% is back towards space. So that's what the greenhouse effect is. The greenhouse effect is literally a warming because some part of the atmosphere, certain ions or certain atoms of the atmosphere act like a blanket keeping the heat in. And it's a good thing because if we didn't have any greenhouse effect whatsoever, the Earth's temperature would be well below, again, what I quoted, I think is 54 degrees Fahrenheit. I think I learned at one point it would be more like 30 or maybe even 18 Fahrenheit or something like that. So if we didn't have any greenhouse effect, we would actually be in a below freezing sort of situation, and that's not good either. But on the same tide, as we'll get into reading a little bit more about this in chapter 19, the greenhouse effect can also run away. And that's what happened, for instance, on Venus. We know Venus at one time probably had an atmosphere much more like ours, but as a result of not obviously not human issues, but just as a result of the chemistry and the effects that Venus was subjected to, it's got a runaway greenhouse effect. And Venus is now the hottest planet, even though Mercury is much, much closer to the sun than Venus. Venus is way hotter. In fact, the surface temperature of Venus is comparable to a pizza oven at Domino's, for instance. So kind of crazy. But all of that's just to talk about how heat is different from internal energy. And it's part of that internal energy is, in fact, kinetic energy of the molecules. But as I've been mentioning a little bit before, there's a lot of different versions of potential or of kinetic energy for a gas. So if you're talking about a gas, you have the individual atoms or molecules, they are, whatever they is what I was going to say. If we're talking about atoms or molecules making up a gas, they have a kinetic energy just associated with the atoms, let's say going left and right. We might call that our x-axis. So that's one kinetic energy associated with just the whole atoms in translational motion. And then the same atoms or molecules could be moving forward and backwards, which we might call the y-axis, and that's another translational kinetic energy that the atoms have. And then another one would be up and down, which we might call the z direction. And in that case, again, that's another translational kinetic energy. But in addition to that, as a molecule, which is made up of multiple atoms, there's the ability of two atoms in a molecule to vibrate basically along the axis of their bonds. That's another form of energy. You can imagine, for starters, since it's vibrating, it must have some kind of energy sloshing back and forth between two different forms, not unlike what we do when we're on a playground swing or something like that. So, in fact, that is the energy sloshing back and forth between potential energy, which you can sort of think of the two atoms as being connected by a spring. So you get a 1/2 kx squared type energy, but you'd also get a 1/2 mv squared type energy where the atoms are actually reaching some peak speed as they come through the equilibrium point, and then they slow down, slow down, slow down, slow down, come to a stop, at which point all their energy is potential energy, which again can be treated like a 1/2 kx squared, even though it's a atomic thing. And then it pushes back out. They speed up, speed up, speed up, speed up, reach their max speed at equilibrium, and then start to slow down, slow down, slow down. And then again, they come to a stop, at which point their energy is completely converted from kinetic energy to potential energy again. So we've got that. We've also got the ability for just the two atoms, like I was showing a second ago, we've got the ability for it to rotate 1/2 I omega squared this way. So that's one other mode of rotation and another version of kinetic energy. Only this one's spinning about an axis, and that doesn't count in the temperature calculation. So when we found that temperature is directly related to the average kinetic energy, that's only those first three I talked about: motion in the x direction, motion in the y direction, motion in the z direction, but not all this other stuff. In addition to the two atoms being able to rotate this way, which is about an axis right through the middle of the screen, we also have their ability to rotate about an axis perpendicular like that. And then we also have the ability for them to rotate like this, which is sort of the bond axis is the actual rotation axis. That one turns out to be almost nothing. In other words, it doesn't come into play because the atoms are so small compared to the size of the bonds, so that the distribution of mass is really, really very close to the axis of the bond. So it's not very relevant. Not only that, you'll see in chapter 19 these other ways at which kinetic energy can be distributed throughout. They don't even kick in a gas until a gas gets above a certain temperature. So it's if you're talking about low enough temperatures and you're talking about, let's say, H2 or N2 or O2 diatomic atoms, if you're talking about those, it turns out that until you get to some critical temperature, they just evidently seem to just move as if they're in this same state right here. So they don't rotate this way, they don't rotate that way, and they don't even necessarily squish back and forth too terribly much until they get to some critical temperature. And then when they get to that critical temperature, then they'll also start spinning about an axis, sometimes two axes, and so on and so forth. So that's all the sort of types of energies that could be in place inside. But I wanted to point out that it's only those three translational kinetic energies that are directly related to the temperature. That's why we got kinetic energy average is equal to 1/2 m times the root mean square velocity squared. But that's also equal to 3/2 kT, where K is the Boltzmann's constant and T is the temperature in Kelvin. So now that we've finished talking about that description of heat and energy transfer versus internal energy, uh, I've also covered internal energy, which is section 19.2. I haven't talked about specific heat, and I'm just going to tell you that that is a measure of how much energy it takes to increase a substance temperature for a given mass and a given temperature change. We'll talk about that in a second. Calorimetry is the problems associated with putting things in contact with one another thermally and finding out what their final equilibrium state is. Latent heat, it turns out that when if you went back to my discussion about the atomic theory of matter, you know that in the solid state, we sort of have atoms as if they're in lattice. You can sort of think of them as like three-dimensional fences. So if you imagine just making three-dimensional fences or even just three-dimensional boxes with just the outer edges, not actual boxes with walls and like that, but literally just the bar that goes from the front right corner to the back right corner on top, and then goes from the back right corner on top to the back left corner, and then goes from the back left corner to the front left corner, and then goes from the front left corner to the front right corner. That's just one little row of bars, if you will, like a jungle gym. And then there's four little bars coming down from each of those one from each of those corners. Those are more of those bars. And then you have an exact replica of the four bars on top on the bottom. And then that repeats itself. So it's not only just, four and four and four around the edges. There's another layer of four behind that, and another layer of four behind that, and another layer behind that, and to the left of that, and to the right of that, and above that, and below that. That's the lattice I'm talking about. Okay, and in front of it too, for that matter. But that's the way atoms assemble themselves generally in the solid state. For instance, we know ice is actually not a very good lattice structure. It turns out that it actually packs the molecules of water sort of not very well, so that it's actually less dense. Water is less dense frozen than it is as a solid. That's why you see when you have a glass of water and you put an ice cube in it, the ice cube pops to the top because the ice as a solid is actually lighter than the ice as a liquid. But either way, with that lattice, we know that the atoms still have to vibrate. That turns out to be a quantum mechanic principle as well. And you could, in principle, tie that to temperature and stuff like that. But we know for a fact how it's tied to temperatures of gases. But they vibrate like that. And if you keep increasing the temperature, their vibrational uh, amplitude, if you will, that vibrational amplitude increases with increasing temperature. And when it increases with an increasing temperature, that means two adjacent atoms in a lattice could get so close to each other that they repel And ultimately, what you could imagine happening is that repulsion's making the equilibrium distance between the two atoms increase. So you see that the two atoms were right here when it was, let's say, 10 degrees Celsius, but now you move it up to 20 degrees Celsius, and now they're like that. Notice they're further apart and their amplitude of oscillation is bigger. And if you keep doing that, that's going to continue and continue and continue until the little bonds that hold them together, one atom to another through that little rod that I told you to imagine, that's actually a bond between the two atoms. And eventually that'll get to the point where that breaks and it's going to get bigger and bigger and bigger at first, but then to ultimately break it, there will be something that we call a latent heat. It's like it's got a certain amount of energy locked up in those bars that are quote unquote pretend that we pretend exist that are holding the atoms apart. And in order for you to completely get them broken apart, you have to add a little kick of energy in. That kick of energy we call the latent heat of fusion. Technically speaking, it's the heat uh, you have to take away in order to make it go from a liquid state into a frozen solid state. So that's what we mean by fusion when you're fusing.
Not sure if that was me.
Uh, it automatically turns off my volume when it does that too. I got to remember that. So,
Yeah,
but thank you. Yeah, I did notice it did that. It's done it every day for the last 4 or 5 days. So luckily, I've discovered that it manages to keep all the file, all the audio and video. So we shouldn't have a problem. We just lost contact for a second.
word.
All right. So that latent heat happens to be latent heat of fusion. When you're talking about the heat you have to extract from the liquid at when it once it reaches the freezing point, it's not good enough to just bring it to a cold enough temperature where you reach the freezing point. You then have to extract more energy from it. The energy called is called latent heat of fusion. Similarly, when you go from a liquid to a gas, in that case, the atoms or molecules are you can sort of imagine that they're about the same distance apart as they were in the lattice, maybe a little bit more, sometimes a little less. But they're sort of also rolling over one another. And for, some long period of time at the microscopic level, which might be literally just microseconds, but maybe for a whole or 1 or 2 microseconds, one atom will be particularly close to only one particular atom while the other ones are sort of moving in and out. It has a specifically fairly strong bond between one atom and one of those other atoms, or sometimes maybe even three or four of those other atoms. And they'll stick around, at least one of them for a few microseconds, and then another one for another few microseconds, and another one. But in order to actually break that up where they really don't automatically reassociate, you have to add in another bit of what we call latent heat. This time it's latent heat of vaporization. And this time you have to put the heat in, meaning, for instance, at water, the boiling point of water at 1 atmosphere is 100 degrees Celsius. It's not good enough to just bring water to the boiling point to make it a gas. You have to then add enough energy to break that, again, sort of bond between adjacent molecules. And that energy is called the latent heat of vaporization. Of course, you can also sublimate like dry ice does. That actually goes straight from the solid state straight to the gaseous state. And therefore, there's also a latent heat of sublimation, which is, quite a bit different from the heat of vaporization or the heat of fusion. And in fact, you might suspect that it would probably be comparable to the sum of the two. And if you have a substance that does both, like for instance, water does, but not necessarily at normal temperatures that we're used to, but that one does, in fact, have the ability to sublimate or to just do the regular transition from solid to liquid to gas. So if you compare all those energies, they should be probably comparable. The sum of the vaporization plus fusion should, if you treat them both positive and add them up, I would suspect they turn out to be roughly the same size as the latent heat of sublimation. Maybe there's some quantum mechanical effects that I don't know about, and that isn't my area of expertise, so I should be careful. I'm just saying that's what I would think as a thinking person with some training in science, though not much in that particular realm. All right. So that's what latent heat is about. Then we'll talk about the first law of thermodynamics. Then thermodynamic processes is sort of the bigger part. We'll talk about specific heat, but instead of it being specific heat as calories per gram degree Celsius, it'll be calories per mole degree Celsius because it turns out when you're dealing with ideal gases, the specific heat of an ideal gas in calories per gram per Celsius degree is shows no real pattern to make sense of. But if you do look at, for instance, the specific heat of a particular gas uh, as a molar specific heat, meaning calories per mole per Celsius degree, there are some very distinct patterns that appear, and that's helpful for us to understand how matter behaves in general. So that's why we talk about the specific molar specific heat in section 19.8. We will talk about adiabatic expansion of a gas. Adiabatic just means a process where no heat is allowed to enter or exit the system. And then finally, we'll get into heat transfer and we'll discuss the three modes by which heat can be transferred, which are conduction, convection, and radiation. We'll have a formula for conduction. We'll have a formula for radiation. It's the Stefan-Boltzmann equation for the radiation. And there's basically just a heat transfer equation for conduction. We don't really have any equations that we study at this level of physics for convection because, as you might imagine, that involves fluid mechanics as well as thermodynamics. So it'd be quite complicated to study. So now that I have that, I think we can go on to begin with our discussion. I think I've covered well enough the difference between heat and internal energy. So I'm going to go ahead on beyond that section. And what I will start off with, though, is this idea right here, which is a very big idea. You might not think of it as a big idea. You probably, like me, think of it as just a conversion factor. But there's something called the mechanical equivalent of heat. So let me start with that. I'm going to go ahead and share my iPad screen with you too, because I just forgot to do that. So I wrote it this way because that's really a better statement of the nature of how big of a deal this is. Uh, at the time that Joule did this, James Prescott Joule, at the time he did this, we didn't really know that mechanical energy and heat were even remotely related. So you can think of it as we've got this unit called the Joule, which you guys learned in 241 for the energy. We use that for kinetic energy and for potential energy, and it turned out just to be the general formula for energy. But more specifically, it was mechanical energy, like I said, talking about the energy of motion that we call kinetic energy, or the energy of position that we call potential energy. Well, at this time, they didn't necessarily have any idea that that energy had anything to do with the energy that we refer to now as heat, which would have been in calories. So James Prescott Joule tried to decide whether that was in fact the case. Was there any relationship? So what he did, you can sort of picture this way. You can imagine that he basically took a container of fluid. Well, that was a particularly bad looking line. Say he took a container of fluid like so, And here's the fluid inside, something like this. And then, of course, what did I? Then, of course, what he did was put a little propeller blade inside of the liquid. And you sort of picture the propeller blade is like this. Well, there's another blade here and another blade here. And then there was some kind of mechanism that would hold the blade. And then there was a coil of string you can sort of imagine as being around the propeller shaft, if you will. And that was run over a pulley and connected to a mass hanging. Okay. So what he did was he basically set up this kind of experiment, and then he would let the mass that's hanging over the pulley here, that mass would fall, and the energy given off would be M times G times H, where the H is the height that it fell through. Now, he also would take and have a thermometer in the liquid at the time. And what he noticed is that, in fact, it caused the liquid to warm up. And we had an equation at that time that said the heat added, if you're assuming all of it goes into changing the temperature of a substance, then the heat that you put in will be equal to M, which is the mass of the substance, C, the specific heat of the substance, times delta T, the change in temperature of the substance. So if he put that equal to mgh, then what he discovered was this, that, like I said, you probably been treating as a unit conversion, 4.186 joules is equal to 1 calorie, or 4.186 kilojoules is equal to 1 kilocalorie, which also happens to be 1 calorie with a capital C, and that's the dietetic calorie that we're used to, is the calorie with a capital C instead of the calorie with the lowercase c. Okay. So this is so much bigger than just a unit conversion. It is a unit conversion, but it was a monumental discovery in that all of a sudden we realized, wait a second, that heat that seems to be like a liquid flowing from one metal or from one substance to another is equivalent to one half mv squared, or it's equivalent to mgh, or one half kx squared, all that good stuff. So it was a really, really big deal, and therefore you should definitely remember these conversion factors. But more importantly, you should remember that, hey, if I were to, for instance, let's just imagine a scenario. This happens to be one that I sort of made the discovery myself because I hadn't read through the appropriate part of the book in time when I took my first physics course. But what I realized was probably there's no more difference than kinetic energy versus heat. And I just on a whim solved this physics problem where the instructor said, you fire a bullet, this is on a test or a quiz or something, but you fire a bullet into a tree and it actually, hits the tree at the muzzle velocity and slows down as it's going through the tree and then comes out the other side. And he gave us the speed there and the muzzle velocity, and asked us how much kinetic energy was lost, something along those lines. And I use that to calculate the increasing temperature of the wood of the tree just by setting the two energies equal to each other. That's what's going on here. We're saying, hey, yeah, kinetic energy can readily be turned into heat. And that's why, for instance, if you rub something enough, it will actually, eventually get a little warmer. In some sense, there is a mechanical energy being applied by you rubbing the thing, but at the same time, that's generating what we call heat, which is the energy that can transfer from one object to another as a result of a temperature difference. Any questions on that? Okay. So as an example, let's try this. I'll say example one. Suppose you run a marathon and get hungry and decide that you have earned the right to eat a very high calorie, oops, left off part of my Y there, a very high calorie dessert. Actually, I think that's two S's. Of 950 calories. How many joules is that? Also, if the body, oh no, was 100% efficient, how high would a 100 kilogram person need to hike to burn those calories? So that's our question. All right. So solution, first thing we got to realize is we're talking about 950 calories for a food item. So I want everybody to remember that that is by necessity the definition of the dietetic calorie, and therefore it's what we call a kilocalorie. So to make this conversion, I'm going to go ahead and say 950 calories is equal to 950 kilocalories. And now I'm going to use our great fact that we got from Joule. And that fact is that basically 1 calorie, lowercase calorie, is equal to 4.186 joules. And of course, the kilo means times 1,000. So I'm going to take 950. Once I turn my calculator on, I'm going to take 950 and multiply that by 1,000 so that I have the right number of calories. So now I have 950,000 lowercase c calories times 4.186. And that gives me 3.977 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 joules. Okay. Now we technically only had probably two sig figs for that 950, so I'll underscore the two sevens to let us know that those are not sig figs. So we're looking at 3.9 million joules. So that's a pretty big result. I'm going to write that down right here. You could of course write it as 3.977 megajoules if you wanted. That would be acceptable as well. Actually, I should write that in red. So that's a lot of calories. Now, the other part they want to know is how high would you need to hike? So what we mean by that, again, assuming 100% efficiency, which is not realistic at all, but what we mean by that is we're going to take M times G times H and set that equal to 3.977 times 10 to the 6 joules and solve for H. So we're going to have 100, which I'm going to treat as 3 sig figs, kilograms times 9.80 meters per second every second times H is equal to 3.977 times 10 to the 6 joules. So H is going to equal, okay, so I'm going to say 3.97, whoa, no, 3976700. I'm going to take that and divide it by parenthesis 100 times 9.80, and that gives me 4,000, oops, 4,057.9 meters. Now we only had 3 sig or 2 sig figs. We used 3 for part of that, but we only had 2 to begin with. So really, I have to call this 4,100 meters, which is, needless to say, that's almost the number of meters that it takes feet to make a mile. So you can imagine this is several miles. Not realistic either because we did it assuming that the body's 100% efficient. Turns out the body's actually a lot less efficient than that. Even if you assume roughly 20% efficient, which is not a unreasonable amount. Uh, I think your book even tells you, yeah, it does take a 20%. So if you imagined it being 20% efficient, then actually only 20% of the energy would go to lifting you. The other 80% would just be wasted by your body. So you could actually get away with doing a little less than 4,000 or 4,100 meters. You could get instead, I'll write it like this. I'll say at 20% efficiency, we just need, what I'm going to do is divide that by zero point 0.8, or actually divide that by zero point 0.2, and that would give me, oh, excuse me, it's supposed to multiply that by zero point 0.2. That would give me more like 811.6 meters. So if the body really was only 20% efficient, then what you basically say is 80% of the energy that came from that 950 calorie bar, 80% of it was not used for it. Only 20% was used, and you'd set that equal to MGH and then solve for the H then. And what I'm saying is, I suspect you should get about 811 meters. Does that make sense, Jennifer? Good deal. All right. So that's a little like the problem in your book. You can check it out. But the big thing is problems like that do require us to recall our knowledge of percents. So I think I'll take a time right now just for a second here and give you a little intro to percents. Just as a reminder. So percent, is part over whole. That's one thing to think about. So what you could do is you could say the number that's left of the percent symbol, if you put that over 100, then you will get the part divided by the whole. And the word part, uh, or I should say it another way. I wasn't planning on doing this, but I realized last semester it didn't work out so well, so I'm trying to do it on the fly, which is not the best thing for teaching, but I'm going to do my best. I have taught math for several years, so hopefully this works out. So what I'll say instead is the part. Oops, I erased some of my words. Didn't mean to do that. Okay, the part. Dang it, why is it doing that? It keeps stealing my pencil colors. The part usually follows the word is, and the whole usually follows of. So when you hear them say the numbers in regular sentences, you can almost always say, okay, well, if they use the word is, they're probably referring to the part. And if they use the word of, they're probably referring to the whole. And that obviously is what goes in the bottom of that equation that I just wrote there. So again, the percent is where you'd write, like if it's 80%, you'd write 80 there, not point 0.8, and the 100 is just there automatically. And then the part goes in the top and the whole goes in the bottom. You should know, obviously, either the part or the whole so that you can get the other. But hopefully that helps you a little bit. That's often what I refer to when my students are having any difficulties because it's really easy to convince yourself, like I did a second ago, that, oh, I need to divide by point 0.8. No, wait, I need to divide by point 0.2. No, wait, I need to multiply by point 0.2. Nope, I need to multiply by point 0.8. This can help you get out of that conundrum. Okay, so hopefully that helps. And we're going to move on to the next section. Do you have any questions on that? Okay. Let me know if you have any problems with percents. That is still an ongoing issue, and I know a lot of our students now have went through that COVID period, and some of the skills and things they might have picked up maybe didn't translate as well as they should have because they were in a less than happy learning environment, so it might have made it a little difficult. So I'm just finding a lot of students have a few little problems with their stuff they're supposed to already know. It might be a result of the pandemic, not like the sickness caused it, but because the teaching situation was bad for a little while. But it might not even be that, to be honest with you. I just want to make sure all my students are following it. So now that I got that, let's go on to the next section, which is where we're going to talk about the internal energy. So as I said, internal energy is the sum total of all the energy of all the molecules in an object. So that's what the internal energy of that object is. Like I said, some people call that thermal energy, but again, the internal energy is the sum total of all energy of all the molecules in an object. We're going to use, like I said, the symbol E with a subscript E, internal. And if you remember what we learned about an ideal gas, specifically, that was a monatomic ideal gas. So we can make some big conclusions about that. So consider a monatomic ideal gas. in that case, in that case, we know that really the only kind of energy they should have, since it's an ideal gas, which remember had those rules in the opening page of chapter 18, where there's no energy between them, there's no attractive forces. The pull balls or the atoms are like pull balls, where they only can interact elastically through collisions with other molecules. Atoms are the walls of the container, which are obviously also made of atoms. So you can think about that and you say, oh, well, in an ideal gas, then really it's just the kinetic energies that are making up the internal energy. And lo and behold, you reach the conclusion that E internal is equal to the total number of atoms that you have, or molecules. In this case, it's atoms because it's a monatomic ideal gas. And the symbol we use for the number of atoms is the capital N. And then we're just going to multiply that by the kinetic energy. And the kinetic energy, remember, is 1/2 mv squared with that bar over it, which means really N times 1/2 m v root mean square squared. Okay. This is a little bit beyond what the book did, in that your book doesn't take the time to tell you that the subscript or that the V subscript RMS is the same thing as the what we're using in the other symbol, where we just put V squared with a bar over it. But hopefully that helps. So that's one of the ideas we can have. Of course, we also learned that the average kinetic energy, K, and since it's average, it's got a bar over it, the average kinetic energy was equal to 1/2 m v squared. Again, they wrote it like this, V squared with a bar over it. What I'm telling you is you can write it as 1/2 m VRMS squared, like that. But we learned in the previous chapter from kinetic theory that this is also equal to 3/2 kT. So we can now make the conclusion that the internal energy of an ideal monatomic gas is 3/2 N kT, where K, remember, is the Boltzmann constant, which is 1.38. And I've always called this 0.7, but it looks like in that time since I learned it, it's become 0.6. So I'm going to try to remember to write it that way. 1.3806 times 10 to the negative 23rd joules per Kelvin. I will also remind you that it is the ideal gas constant divided by Avogadro's number. So in some sense, if you remembered 8.314 and you know Avogadro's number is 6.022 times 10 to the 23rd, you don't have to memorize another constant, the Boltzmann constant. Okay. So does that make any sense to you, that that might actually be the internal energy of an ideal monatomic gas? You can actually put it either of these ways, really. Okay. So ultimately, we could also recall that the ideal gas law, P, well, also PV equals nRT, and PV we learned was also equal to NKT, like that. So you can also realize that the E internal can also be written as E internal is equal to 3/2 N times R times T. So all of that is completely fair and reasonable, and this is an expression for an ideal monatomic gas. Okay. So your book goes on to tell you and let you know about, when you go on to just a little bit more complex of a gas or a substance, you'd have to talk about at least a diatomic gas. So a gas that's made up of two atoms per molecule. And in the case of hydrogen, nitrogen, and oxygen, it's two identical molecules. That's sort of the simplest next step up. And when you do that, you see that, of course, the two masses can spin about an axis right through the middle. And it could be like this one where the axis is straight in and out of the screen, but it could also be where this axis is up and down, so it could spin that way. Each of those are called degrees of freedom. We'll use the symbol F for that. What I try to teach my students is something one of my instructors told me that I thought was quite ingenious, even though I'd never seen it written down. But it's sort of the number of variable squared terms you have in an energy equation. So, for instance, all the different energies that end in some variable squared, like 1/2 mv squared. That's v squared, so that's the square of velocity. That's one of those terms. You have a degree of freedom for that. There's also 1/2 I omega squared for, rotation about the axis going through the middle of the screen, perpendicular to the screen. That's 1/2 I omega squared. That square variable means there's another degree of freedom. Then you have a 1/2 I omega squared for the axis going straight up and down for that one. So that's a third degree of freedom. We already had the 3 degrees of freedom associated with translational motion left, translational motion up, and translational motion back and forth. So we're up to 6 degrees of freedom already. So think about that. That comes in handy when we're talking about all the possible energy that something might have as a gas in general. But even if you restrict yourself to an ideal gas, if you're not restricting yourself to monatomic, then you're going to have to introduce more degrees of freedom. Not that they have anything to do with the temperature. It's only those 3 translational modes of the temperature of the kinetic energy that is equivalent to temperature. So the more of those degrees of freedom a given substance has, and by the equipartition theorem, which is something you're also going to learn about, it turns out that the number of degrees of freedom you have, because there's such a large number of atoms or molecules. Remember, we're talking Avogadro's number. So, at least 10 to the 23rd is Avogadro's number, but even 10 to the 18th or 10 to the 20th or 10 to the 26th, those are huge numbers. So statistics that you apply to such large numbers should be super, super accurate. And because of that, if you've got 12 degrees of freedom for a particular substance, then you're trying to fit 10 to the 23rd or maybe even 10 to the 22nd or something uh, atoms into those 5 degrees of freedom. The odds that any one degree of freedom has more energy than any other is essentially nil. So what that means is each degree of freedom gets the same amount of energy. So when you put, let's say, 500 joules of energy in, then 100 will go to 1 degree of freedom, another 100 will go to another 100 will go to the third, another 100 will go to the fourth, and the last 100 will go to the fifth. There's never going to be any deviation from that. Therefore, if you're talking about something that has 5 degrees of freedom, and you apply heat to it, water's a case in point where you'd have maybe 6 or 7 even, then basically all but 3 of those degrees of freedom are increasing their energy without increasing the temperature at all. So only the 3 of them are related. So in that case, you're getting 60% of all the energy put in goes into changing the temperature, but the other 40% goes into doing something else. And therefore, that substance that has 5 degrees of freedom is going to act like a substance that is uh, I would say is a good insulator because 40% of its energy is not increasing the temperature. Only the 60% is. And if you found one that had 12 degrees of freedom, then 9 of the 12 would be the parts of the energy that aren't going to change in the temperature, and only 3 of 12, which is about 25%, would be able to go into changing the temperature of the substance. So that's what we're getting at there when we're talking about degrees of freedom and diatomic and polyatomic molecules and so on and so forth. Any questions on that, Jennifer? Do you go by Jen or Jennifer? I normally call people the whole name, but
It's usually Jen, but
okay.
whatever, it doesn't
It feels
matter.
more comfortable for me to say Jen. That's why I was asking.
Easy.
All right, so let's look at another example. I'm going to call this example two. And example two is basically how much heat input is needed to raise the temperature of an empty 20 kilogram vat made of iron from 10 degrees Celsius to 90 degrees Celsius. So, how much energy, or let's say heat input, that's how much heat is required to bring a 20.0 kilogram empty iron vat from, oops, 12.0 degrees Celsius to, let's say, to 95, darn it, to 95.0 degrees Celsius. So that's a problem, very much like the one in the book, slightly different, but not too terribly much. Uh, and in order to do this, I've already given you the equation. If you remember back here, this was an equation, though I didn't box it off at that time. Actually, I should stop that right there. This part right here is the equation that I'm using. So Q equals MC delta T is what we're shooting for. So I'm going to go ahead and say solution. Formula we're using is Q equals MC delta T. The M is equal to 20.0 kilograms. The C is really the specific heat, and that's actually a lowercase c. Let me write it a little smaller so there's no confusion. Specific heat is heat per mass or heat per mole or something like that. And we generally reserve the lowercase symbols for such quantities that are specific, meaning they've been per unit mass or per unit mole or something like that. So that's why I'm making a big point to say that. Now, if you look up the specific heat of iron, for instance, there's one in table 19.1. So I'm going to put that right here, table 19.1. And when I look up iron, I see that it's 450 calories. That's a lowercase c again. Calories. Actually, that's the joule one, my fault. Yeah, I wrote the joule one by mistake here. So 450 joules per kilogram Celsius degree is the specific heat. And then T initial is 12.0 degrees Celsius and T final is 95.0 degrees Celsius. So we're asked to find Q. That means Q is equal to 100, or excuse me, 100 was the last person we were solving a problem for. It's 20.0 kilograms, 3 sig figs, times 450 joules per kilogram. Notice that the use of the joules per kilogram was actually a better choice anyways because we had the mass in kilograms and the 450 came in joules per kilogram. And then the delta T, remember delta, unless we explicitly tell you otherwise, in physics or in chemistry, delta always means final minus initial. So I'm going to do 95.0 degrees Celsius minus 12.0 degrees Celsius. And again, this should allow us to get 3 sig figs. So I'm first going to do 95 minus 12, and that gives me 83.0. I'm multiplying that times 20, and then that times 450, and that gives me 7.47 times 10 to the 1, 2, 3, 4, 5 joules. So the heat it will take is 747,000 joules. Now, example 3, what if that was filled with water? So example 3, what if the vat was filled with 20.0 kilograms of water? Okay. So this is the same problem, only now we've got two things that we got to heat up. We got to heat up the steel and we got to heat up the water. And of course, the water, which you might not recognize, remember, well, I didn't even tell you this. In my other class, I told everybody that the specific heat of water was the definition of the calorie. So we define the calorie to be the amount of heat required to bring 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Very specific determination there. It has to be from 14.5 degrees Celsius to 15.5 degrees Celsius, 1 gram of water. And that turned out to be the definition of 1.000 to any number of decimal places of calories. So it might not seem to you that water has a high specific heat because it's one, but on that same scale, the specific heat of aluminum is 0.22. The specific heat of copper is 0.093. The specific heat of iron is 0.11. So these are really small. So I'm going to go ahead and do the calculation. Q is equal to, now in this case, notice the delta T and the M do not change. So I'm going to pull them out in front and I'm going to say 20.0 kilograms because it's 20 kilograms of steel and 20 kilograms of water. So the other part is the 95 minus 12, and that is 83.0. And that Celsius degrees, which we put the degree after the Celsius to show us that that's already two temperatures that have been subtracted from one another. And now what's going to happen is that's M and delta T. So I've got to take the specific heat of iron, which we already learned was 450 joules per kilogram Celsius degree, and add to it the specific heat of water, which in this case as a liquid is 4,186 joules per kilogram Celsius degree. And this time it's going to be quite a bit bigger. So I'm going to say 20 times 83.0 times parentheses 450 plus 4186 close parentheses. That gives me 7.70, actually 7.70. That's still a sig fig actually, times 10 to the 6 joules. So it's a whole power of 10 higher when we included the water. Okay. And that gives you some idea of how much of a difference water can make. I've already mentioned to you guys, for instance, that the nation of Great Britain, the UK or whatever, they're essentially an island. But if you look at it on a map or a globe, you'd see that their latitude is comparable to large swaths of the latitudes of Canada. So you might think Great Britain and Canada should have similar temperatures and similar climates. But it turns out Canada is a lot colder than Great Britain, and Great Britain, which sort of has the weather that's not unlike, Washington State and Oregon for in regards to rain, but in terms of temperatures, it's more like the mid latitudes of California or even somewhat like what we have in Virginia and stuff like that. And that's because the specific heat of water, which the island of Great Britain is completely surrounded by, that maintains the temperatures at a much more moderate climate. So it doesn't get as hot, nor does it get as cold. There's a lot of neat things that are a result of the high specific heat of water, but it does make it a explicitly really good insulator. Of course, the downside is if you actually use that as an insulator in your house, it would cost millions of dollars because it turns out even if you make a wall that you wanted to fill with water and it's only a 2x4 wall, if it was a 2x4 wall, meaning it's only about 3.5 inches thick, and you fill it up with water to 8 foot high, which is the typical height of a ceiling. Some are 9, but most of them are bare minimum 8. It takes every bit as much strength to hold back 8 foot of water with only 4 inches behind it as it does for Olympic-sized swimming pool that's only 8 feet deep. It turns out only the depth is what matters about how strong the wall would have to be to hold the water in. So, yeah, it's not very convenient for us to use water as an insulator in our houses. Any questions on that? Okay. Your book makes a really neat little conceptual example here. It says you accidentally make a bad mistake letting an empty iron frying pan get very hot on the stove, 200 degrees Celsius or even more. What happens when you dunk it into a few inches of cold water or cool water in the bottom of the sink? Will the final temperature be midway between the initial temperatures of the water in the pan? Will the water start boiling? Assume the mass of water is roughly the same as the mass of the frying pan. So we already learned that the iron skillet has a specific heat, for instance, of about 450, whereas the water has a specific heat of 4,186. So that's like almost a whole factor of 10 higher. So no, you would not expect them to reach the common temperature that's midway between the temperature of the water and the temperature of the frying pan. It's going to be way closer to the temperature of the water. It says experience may tell you that the water warms up perhaps as much as 10 or 20 degrees. The water doesn't come close to boiling. The water's temperature increases a lot less than the frying pan's temperature decrease. Why? Because the mass of water is roughly equal to that of the pan, and iron has a specific heat nearly 10 times smaller than that of water. As heat leaves the frying pan and enters the water, the iron pan's temperature change will be about 10 times greater than that of the water. If instead you let a few drops of water fall onto the hot pan, that very small mass of water will sizzle and boil away. The pan's mass may be hundreds of times larger than that of the water drops. So if you've ever done that, that is one of the tests, for instance, they use to check whether your frying pan is hot enough to begin cooking. Is normally to tell you to throw oil on it, and it should skedaddle across the top. That's part of what we call the Leidenfrost effect, where basically there is sort of some boiling at the bottom level, and that produces a gas that is sort of like an envelope between the liquid and the solid, and it allows a nearly frictionless surface for the water to skitter across, or the oil in that case. So I think that's a pretty neat question anyway, so we'll do that. I will tell you now, since we're about out of time, we only got 2 minutes left. There's another equation you need to start using. And we already learned, for instance, Q is equal to MC delta T, which is, of course, M times C times T final minus T initial. I just wanted to remind you that's what T is. But it turns out that, as I told you earlier, when you put heat to something to bring it to a change of phase, what happens is it starts once it reaches that critical temperature, like the boiling point of water, all of the water will stay at that boiling temperature, 100 degrees Celsius if we're at 1 atmosphere, and it'll stay 100 degrees Celsius, period, for a long period of time up until it all basically boils away. And what's happening is it's waiting for the latent heat to kick in. So you might want to find out what's the formula for taking into account the latent heat. Well, that formula is Q is equal to M times L, where L is the latent heat. And what I tell my students to do is when they're trying to solve calorimetry problems, there's a couple ways you can do it. You can say the sum of the heat going in plus the heat going out is equal to zero. I don't like using that because you have to be very specific about using signs. So I use this one. I write on the left-hand side uh, the heat that's leaving the hot object. And then on the right hand, oh, that's the left hand side. Then on the right hand side, I put the heat that's leaving the cold stuff. So for instance, if you were trying to calculate what the final temperature of a water aluminum cup is after you take a 100 degrees Celsius chunk of aluminum and put it in 50 grams of water in a 12-gram aluminum cup, then the hot side is just the aluminum block that was 100 degrees Celsius. So you got MC delta T. And in this case, you're going to make sure, even though that temperature is going down, you're not going to use the delta T. You're going to use big temperature minus final temperature because using this form, you have to have all positive terms. So you don't use just blindly delta T is T final minus T initial. You actively choose to make it a positive number. So in the case of the hot metal, it went from 100 degrees Celsius, which would have been the initial temperature, to on the order of 20 degrees Celsius. So you'd actually do 100 minus 20 instead of 20 minus 100. Then on the right hand side, you would put the mass of the cup, which is made of aluminum 2, and the specific heat of aluminum. And that one is actually cooling down. So you can do T final minus T initial. And then you do again for the mass of the water. And again, you do T final minus T initial. So those two terms would be on the right and only the aluminum would be on the left. That should get you good enough to doing to start doing the calorimetry problems, even though I haven't shown you any examples of them. And we'll finish this up next time. In addition to that, we'll be covering all those different phases or all those different processes and stuff. That's going to help us a lot in chapter 20. So thanks for coming, Jen.
Thank you. Good night.
Good night. Have a good one and have a nice weekend. I don't know if you turned in your syllabus sheet yet, but make sure you do if you haven't.
I did way on in the semester.
Okay, cool.
Okay.
Well, have a good weekend and feel free to text or email if you need any help or if you just have some problems you're trying to work or something like that.
Okay, will do. Thank you so
All right.
much.
Thank you. Bye-bye. All right, so that's about it. See you later, folks. Bye bye.